So, back in 1983, there was this Boeing 767 carrying 69 people, right?
Yeah, cruising at like 41,000 feet over Canada.
Exactly. And suddenly, an alarm goes off in the cockpit. The left engine just completely dies.
Which is terrifying. And then just a few minutes later, boom, the right engine dies too.
Right. This massive commercial airliner weighing tens of thousands of pounds is just completely out of gas. It basically turns into a giant, unpowered glider falling out of the sky.
And the wild thing is that it wasn't a mechanical failure at all.
No, not at all. It wasn't a leak in the fuel tanks, and it wasn't sabotage. The culprit was actually a language barrier.
But not like English or French.
Right. It was the language of science.
Yep.
A really simple misunderstanding of measurement units on the ground caused the plane to be loaded with less than half the fuel it needed to reach its destination.
It's just a terrifying example of what happens when the rigorous framework of scientific communication breaks down.
It really is. And we're going to explore the mechanics of that specific disaster a little later, but it perfectly illustrates why the topic we're unpacking today is not just, academic theory. It is quite literally the infrastructure of reality. Welcome to the deep dive.
So today we have a very specific mission. We are looking at a foundational text. It's a chapter titled Exploration, Entering the World of Secondary Science.
Now, I know what you might be thinking listening to this. A secondary science textbook.
Yeah, you're probably thinking, well, we already know basic physics and biology.
Exactly. But our goal here isn't to teach you what a proton is. Our goal is to examine the pedagogy of scientific thought.
Right, we want to look at how we actually teach the human brain to move from that basic childhood wonder to, rigorous empirical investigation.
And to do that effectively, we're adopting a unique format for this deep dive. We aren't just going to offer a breezy, high-level summary of the concepts.
No, we're actually going to read the exact original text from the source chapter, step by step, paragraph by paragraph.
And then we're going to immediately break it down, translating that pedagogical structure into plain conversational language. No skipping, no shortcuts.
Yeah, we are tracing the intellectual journey from pure curiosity to the deep, rigorous exploration that defines human progress.
The beauty of slowing down to chew on the original text like this is that you get to see the architecture of scientific epistemology. Yeah. How we actually know what we know.
Exactly. By the end of our time today, you will have a comprehensive line-by-line understanding of the philosophy of scientific modeling.
Right, and the crucial necessity of standard units, the mechanics of estimation, and why deliberate ignorance is actually the secret weapon of the world's greatest thinkers.
So let's jump straight in. The chapter sets the stage by defining a massive paradigm shift in how a student is expected to view the universe.
Okay, I've got the text here. It states, quote, "In the middle stage, science invited you to be curious and observe the world closely, to ask questions, and to find out how things work."
Right, setting the baseline.
Yeah. Then it says, "In our journey, we discovered that science began with wonder and grew through careful experiments. We connected ideas across the world of the living and non-living."
A very observational phase, basically.
Yeah, exactly. But then it shifts. As you now enter the secondary stage, this journey continues, but with an emphasis on deep exploration. Science is not only about what we know, but also about how we know it.
That's the crucial pivot right there.
Totally. It goes on how observations lead to measurements, how patterns are expressed using symbols and equations, how models are built to represent complex systems, and how ideas are tested, often revised, and sometimes even discarded.
Wow, yeah, that is a huge leap in methodology.
It finishes with, in our secondary stage, textbook of science exploration, we will look more closely, think more carefully, and find out how scientific ideas help us make sense of nature, technology, and our place within them.
So that paragraph is doing a lot of heavy lifting. It's essentially outlining the evolution of human cognition. Well, it draws a stark line between the middle stage and the secondary stage. The middle stage is phenomenological. It's purely observational.
Like you hold a magnet to a pile of iron filings, the filings jump up, and you just experience wonder.
Exactly. You ask, what is happening? You are connecting ideas broadly. But the secondary stage fundamentally alters the contract between the student and the universe.
Right. The demand shifts from, what is that, to prove to me the mechanics of why and how that happens, and show me your measurements.
It feels akin to the progression of learning to cook, but moving from the dining room into the commercial kitchen.
Oh, I like that analogy.
Yeah. In that middle stage, you are just tasting the food. You bite into a cake and say, wow, this is incredibly sweet and fluffy. You might generally know that flour, eggs, and sugar are involved. It's qualitative.
But when you move to the secondary stage, you become the pastry chef.
Exactly. Qualitative observation is no longer enough. You need quantitative reality.
You need to know that baking powder requires a specific liquid and heat to trigger a release of carbon dioxide gas, which creates bubbles in the batter. You need the exact grams of sugar, the precise temperature.
And I appreciate that analogy because it highlights the transition to methodology. The text explicitly points out that science is not only about what we know, but how we know it.
Right, the recipe.
Yeah, that how is the recipe. And notice a very specific phrase the authors include: how ideas are tested, often revised, and sometimes even discarded.
That's tough.
Uh-huh.
That is arguably the most difficult psychological hurdle for a new science student.
Oh, totally. You have to abandon the idea that a textbook is a static collection of eternal truths. You are entering a discipline that is inherently destructive to its own ideas. If the experiment fails, the idea is discarded.
So, to help the student navigate that rather intimidating process of testing and discarding ideas, the book introduces a visual theme for the entire curriculum.
Yeah, let's look at how they frame this.
Okay, the text reads, quote, "To reflect the approach of this textbook, the page numbers have been thoughtfully designed and are framed by a magnifying glass and a compass."
It's a nice visual.
It is, continues. The magnifying glass symbolizes careful observation, noticing patterns and paying attention to what might otherwise be missed.
Okay, so the empirical side.
Right. And then the compass reminds us that exploration also needs direction, choosing appropriate models, asking the right questions, and knowing the limits of where our ideas apply.
A really vital counterbalance.
And it concludes, together they tell us that exploration in science is not wandering aimlessly, but trying to make sense of our world with care and purpose.
I think it is an elegant visual metaphor for the dual nature of scientific inquiry. The magnifying glass represents the empirical side, the data collection.
Right, zooming in.
Exactly. When you look through a magnifying glass, you are intentionally restricting your field of vision to focus intensely on a micro-level detail. You are looking for anomalies, for recurring patterns in a leaf, or the crystalline structure of a rock. It requires immense patience and hyperfocus.
But, the inherent danger of a magnifying glass is myopia, isn't it?
Yeah, definitely.
If your entire worldview is restricted to what you can see under a 10x lens, you are going to spend your life crawling around in the dirt, completely lost.
Huh.
You might have a massive spreadsheet of highly accurate data about the dirt, but you have no idea what forest you're in.
Which is precisely why the compass is introduced as the necessary counterbalance. The compass represents the theoretical framework. It is the hypothesis.
It gives you direction.
Right, before you ever get on your hands and knees with the magnifying glass, the compass tells you which direction to walk. It forces you to ask, why am I collecting this data?
As the text points out, it represents knowing the limits of where our ideas apply. The compass keeps you from wandering aimlessly through infinite data sets.
This implies that to use a compass effectively, you have to have a map. You need a representation of the territory you are exploring.
And in the realm of science, those maps are called models. Which brings us to section 2, which I find to be the most counterintuitive yet brilliant concept in the entire text.
The necessity of deliberate simplification. Let's read the opening of this section.
Okay. The book states, "The natural world is complex, and studying it in full detail is often impossible. To make sense of this complexity, science uses models."
Setting up the problem and the solution.
Yep. These are simplified ways of looking at real systems that focus only on what is most important for a given question. In physics, a moving car may be represented as a single point, while in chemistry, atoms and molecules are drawn as spheres and bonds.
Right, distilling things down.
In biology, cells are shown as diagrams highlighting key parts. And in earth science, the Earth may be treated as a smooth sphere layered into distinct regions.
And here comes the really important part.
Building such models involves making assumptions and deliberately ignoring certain details. For example, when studying the motion of a falling object, air resistance may be neglected to understand the basic effect of gravity.
Yeah, ignoring reality.
It goes on, in biology, when studying how the heart pumps blood, many individual cells are ignored so that the organ can be understood as a functioning system. Remember that these choices are not mistakes. They're done on purpose to keep things simple enough, but still allow us to find answers to what we are looking for.
I really want to pause and emphasize that phrase, deliberately ignoring certain details. We spend our entire lives being told to pay attention to the details. Carelessness is framed as a moral failing.
Totally.
Yet, here's a foundational science text arguing that the secret to understanding the universe is actually learning exactly what to ignore.
It is a profound epistemological stance. The text justifies it immediately. The natural world is complex, and studying it in full detail is often impossible.
Let's take that falling object example. If you drop a tennis ball from a building and you try to calculate its descent by factoring in the aerodynamic drag of every single microscopic fiber of fuzz on that ball,
Oh man, the math would be insane.
right, you'd have to include the slight variations in air density at every millimeter of its fall, the gravitational pull of the moon at that exact second. Your equation would be millions of variables long.
You would literally never be able to solve it just to find out how fast the ball falls.
Exactly. By stripping away reality, by pretending the ball is falling in a perfect vacuum, you isolate the core variable gravity. Ignoring reality is a feature, not a bug, of scientific modeling.
It really reminds me of looking at a subway map.
Oh, that's a good one.
Yeah, if you travel to London or New York and look at the transit maps, there are these beautiful, clean, minimalist diagrams. The colored lines run perfectly straight. They turn at pristine 45 or 90-degree angles, and the stations are spaced perfectly evenly apart.
But does the actual physical tunnel under the city look like that?
Absolutely not. The real tunnels curve haphazardly. They dip to avoid ancient sewer lines. They bend around bedrock. But the map deliberately ignores all of that physical reality.
Why? Because the given question, as the text frames it, is simply, how many stops until I get to Times Square?
Right. If the map showed you the literal to-scale geographical reality of the tunnels, it would be a tangled, unreadable mess. It would be useless.
The subway map is the quintessential model. It sacrifices geographical accuracy to maximize functional utility. And the text gives us another great example of this, reducing complex entities to simple shapes.
Yeah, the car example.
Right. It mentions treating a moving car as a single point in physics. When a physicist calculates the braking distance of a Honda Civic, they do not care about the color of the paint, the radio station playing inside, or the leather seats.
The car is conceptually crushed down into a single dimensionless dot that has only two properties, mass and velocity.
Let's see how the textbook trains the student to perform this conceptual crushing with a real-world scenario.
Okay, here's the example from the text. Example 1.1, a cricket shot. Think of a cricket ball being hit for six. You want to make a simple model.
Okay, so a ball flying through the air.
What details would you include? What would you ignore? Answer. We must ask, will the ball cross the boundary without hitting the ground first?
There is the compass question.
Right. It continues. For this, things like the brand of the bat, the color of the ball, the amount of grass on the field will make no difference. On the other hand, the mass of the ball and the speed and direction in which it has been hit will be very important.
Exactly, isolating variables.
Air resistance, the spin of the ball, and the stitching of the threads at the seam have smaller effects that can be ignored in a simple model. As we build more and more complex models, we add extra details for greater accuracy.
This exercise is all about establishing the compass heading. The compass question is, will it cross the boundary? Once that specific goal is set, you can violently prune the variables.
Does the color of the leather impact the parabolic arc of the ball? No. Toss it.
Does the brand of the bat matter once the kinetic energy has been transferred to the ball? No. Toss it. You are left with the core kinetic variables, mass, speed, and direction.
But I'm fascinated by the caveat at the end. The text notes that things like air resistance and the stitching on the seam can be ignored for a simple model.
Right, a simple one.
But if you were, say, a data scientist working for a professional sports broadcasting network, building a multi-million-dollar simulation to predict exact trajectories, your model's required accuracy would be much higher.
So you would add those variables back in. The model's complexity scales precisely with the demands of the question.
Let's actually test this framework. The textbook provides a mental activity immediately following that example.
All right, let's hear it.
The text reads, Activity 1.1, let us model. Suppose you ride a bicycle from your school to your home. You want to model the time it takes to go home from school.
Okay.
What details would you keep? What details could you ignore? Suggest why ignoring some details may actually be useful.
Okay, I'll play the student here. The compass question is, how long is my commute? To build the absolute base model, the undeniable variables I must keep are the total distance of the route and my average speed while pedaling.
That gives you your primary equation time equals distance divided by speed. Now, apply the deliberate ignorance. What are you tossing out?
I'm tossing out the brand of the bicycle. I'm tossing out the color of my helmet. I'm tossing out the ambient temperature, assuming it's not, like, extreme enough to stop me.
Right. But the text asks why ignoring some details is useful. I think the prime example of a variable to ignore here is wind speed and direction.
That's an interesting choice. Wind clearly affects the speed of a cyclist. A headwind slows you down, a tailwind speeds you up. Why would you argue for ignoring a variable that directly impacts your commute time?
Because wind is a chaotic system. It's not a constant. It gusts, it dies
Right.
down, it swirls unpredictably around buildings and trees.
Okay, fair point.
If I wanted to build a model that included the aerodynamic drag of wind, I would need a continuously updating data set of wind vectors for every single meter of my route. The mathematical complexity required to process that data would be staggering.
Right. By the time you solve the equation to find out your commute time, you could have just ridden your bike home.
Exactly. By intentionally ignoring the chaotic variable of the wind, I accept a slight margin of error in exchange for a highly functional, immediate baseline answer. It will take roughly 15 minutes.
That is a spectacular defense of the utility of simple models. You correctly identified that overcomplicating a model can paralyze its usefulness. And this exact principle of radical simplification isn't just for bicycles and cricket balls.
It's for the cosmos, right?
Yes, it is the very method used to decode the cosmos. The text highlights a historical figure to prove this.
Ah, yes. The text reads, "Meet a scientist, simplifying the stars." Science often begins by ignoring details. When physicist Meghnad Saha studied the light from stars, he did not try to model every atom, every reaction, or every movement inside a star.
A seemingly impossible task otherwise.
Totally. Instead, he treated the matter in the star as a hot gas, ignored many complex processes, and focused only on temperature, pressure, and how atoms formed ions. This simplification allowed him to explain how the color of stars is deeply connected to their temperature.
Let's provide some context for how monumental that simplification was. A star is arguably one of the most complex environments in the universe. It is a titanic, churning nuclear furnace.
Pure chaos.
You have magnetic fields twisting and snapping. You have intense radiation pressure fighting against the crushing gravity of the star's own mass. You have convection zones boiling with plasma. You have trillions of atomic collisions happening every fraction of a second.
And yet, Meghnad Saha approaches this apocalyptic environment and decides to model it as essentially a simple balloon filled with gas.
It is a breathtaking act of scientific audacity. By aggressively ignoring the magnetic fields, the convection currents, and the nuclear fusion mechanics, he distilled the star down to 3 thermodynamic variables: temperature, pressure, and ionization state.
And because he cleared away all that chaotic noise, he was able to spot the elegant underlying pattern. He proved the correlation between the chemical makeup we see in the light spectrum of a star and its surface temperature.
Right.
He gave us the ability to look at a blue star and know it is vastly hotter than a red star simply by analyzing the light. That discovery doesn't happen if he gets bogged down trying to model a billion individual magnetic field lines.
But Saha's breakthrough introduces the next pedagogical challenge. Saha was an Indian astrophysicist working in the early 20th century. If he builds this stripped-down, highly specific model of a star, how does he communicate that model to an astronomer in Germany or a physicist in America without the nuance being lost in translation?
They need to ensure they're all talking about the exact same variables.
They need an incredibly rigid, standardized language. And that is exactly what the textbook tackles in Section 3.
Let me grab that section. It reads, "As you explore science more deeply, you will notice that it uses language in a very careful and precise way. Many words that we use in everyday life, such as force, work, cell, or reaction, have specific meanings in science.
Right, taking common words and locking them down.
These meanings are often very specific, because scientific ideas must be communicated clearly and unambiguously. To allow scientists across the world to describe observations, compare results, and build ideas together, science uses a shared language of these specific terms, symbols, and units.
The global standard.
Quantities, such as mass, velocity, force, and electric current, are represented by symbols like M, V, F, and I, each associated with a defined unit.
The transition from everyday language to scientific language is a major stumbling block for students. We are used to language being fluid, poetic, and context-dependent, but in science, ambiguity is the enemy.
The text points out words like work and force. In standard English, the word work is endlessly elastic. You go to work at an office, a painting works well in a living room, you work up a sweat.
But if you walk into a physics classroom, that elasticity vanishes. The word work is placed into a mathematical straitjacket. In physics, work is defined strictly as a force causing the movement or displacement of an object.
Right. Work equals force times distance.
Exactly. If you stand in front of a concrete wall and push against it with all your might for 5 hours until you physically collapse from exhaustion, in everyday language, you did a massive amount of work.
But a physicist would look at you and say, the wall didn't move a single millimeter. Therefore, the distance is zero. Force times zero is zero. You did zero work.
It sounds pedantic, but that pedantry is what allows the global scientific machine to function. When a researcher publishes a paper claiming a certain amount of work was done by a machine, every other scientist on the planet knows exactly what physical parameters are being discussed.
There is zero room for subjective interpretation. And to make this communication even more efficient, they abandon the words entirely and replace them with universally agreed upon symbols. Me for velocity, it becomes an international shorthand.
Which brings us to the elephant in the room for so many people approaching science, the math. Let's read how the textbook frames this, because it is genuinely one of the most empathetic explanations of mathematics I've ever seen.
Oh, absolutely. It states, to make this even more precise, science often turns to mathematics to allow relationships between quantities to be expressed clearly and tested carefully. This can sometimes feel challenging, but it is important to remember that mathematics in science is not meant to be a hurdle.
That's such a comforting sentence.
Right. Instead, it is a language that helps us think more clearly about the world. An equation is not just a calculation tool. It is a compact statement about how certain things are related.
A compact statement. I love that.
For example, describing motion using quantities, such as distance, time, and velocity, allows us to answer questions about where an object will be at a later moment. In the same way, mathematical expressions are used to describe rates of chemical reactions, patterns of population growth, or changes in energy within a system.
And here comes the pedagogical advice.
Learning to use mathematics in science does not mean memorizing equations. It means understanding the situation first, identifying relevant quantities, and then using mathematical relationships to reason carefully.
Understanding the situation first.
In this way, mathematics becomes a powerful language for thinking, not just for finding numerical answers. If you focus first on understanding the situation and the quantities involved, equations will begin to feel less like obstacles and more like helpful guides in your exploration of science.
I cannot emphasize enough how critical this paragraph is for a student's development. It actively attacks the trauma that so many people associate with math.
Yeah, math is heavily stigmatized as a filtration system, a series of arbitrary hurdles designed to weed out the people who aren't smart enough.
The textbook shatters that myth. It redefines mathematics simply as a compact statement. It is a translation of a physical reality into the most efficient language ever devised.
I completely agree with this sentiment, but I have to push back a little on the reality of the classroom experience. The text says, learning to use mathematics in science does not mean memorizing equations. But in practical terms, countless students spend the night before a physics exam doing exactly that rote memorization of formulas.
Yeah, that's true.
How do we actually bridge the gap between this idealistic view of math as a helpful guide and the panic of staring at a page full of Greek symbols?
Well, the key is embedded right in the middle of that paragraph. It means understanding the situation first. That is the vital sequence of operations. The failure happens when a student tries to memorize the equation before they understand the physical reality it describes.
Right.
Let's take the classic equation, force equals mass times acceleration, F equals ma. If you just memorize those letters, it's meaningless algebra. But if you first visualize the situation, imagine pushing a shopping cart.
Okay.
If the cart is empty, so low mass, it is very easy to make it speed up, high acceleration with a small push, the force.
Makes perfect sense intuitively.
But if the cart is filled with 100 bowling balls, massive mass, that same small push will barely make it move, low acceleration. You intuitively understand the physical relationship.
Right.
The equation F equals ma is just the absolute shortest way to write down that exact story about the shopping cart. When viewed that way, the equation isn't an obstacle, it's a perfect summary.
So the math is the universal language. But what happens when people speak different dialects of that language? What happens when the standard units are ignored?
Back to the airplane.
Yes, we hinted at this in the introduction, but the textbook provides a harrowing real-world example of why unit standardization is non-negotiable.
Let's hear the textbook's version of it.
It reads, ready to go beyond. airplane fuel miscalculation.
Yeah.
In a well-known incident, a passenger aircraft ran out of fuel mid-flight due to a mix-up in units.
The Gimli glider.
The flight needed 22,300 kilogram fuel in total, but the ground crew miscalculated the fuel required since they used the density of fuel in pounds per liter rather than kilograms kilojoule per liter.
A massive air.
The aircraft was about 15,000 liters short of fuel and luckily could glide to an emergency landing, which damaged the aircraft, though there were no casualties. Pounds and kilograms are very different.
Very different.
Using standard units, SI, everywhere avoids conversions and errors. Why is a kilogram used everywhere? When we buy rice or vegetables, we expect a kilogram to mean the same amount everywhere.
That's the standardization part.
Imagine the confusion if we use different weights everywhere. Thankfully, measurements are based on agreed international standards, not local objects or opinions. Standard units allow scientific results to be compared and ensure fairness in daily life and trade.
Like we said earlier, this refers to the infamous Gimli glider incident of 1983, Air Canada Flight 143. It is perhaps the most dramatic endorsement of the international system of units, SI units, in human history.
Let's dig into the mechanics of that failure, because it's fascinating. The aviation industry in Canada was in the middle of transitioning to the metric system.
Right.
The plane required 22,300 kilograms of fuel.
Right.
The ground crew measured the fuel volume they already had in the tanks, which was in liters, and they needed to convert that volume into weight to know how much more to add. But instead of using the conversion factor for kilograms per liter, they used the conversion factor for pounds per liter.
And a pound is less than half the mass of a kilogram. It's roughly 0.45 kilograms. So the ground crew ran the math, the numbers looked correct on the clipboard based on their flawed conversion factor, and they loaded what they thought was 22,300 pounds of fuel, mistakenly believing they had loaded 22,300 kilograms.
So the aircraft took off with roughly 45% of the fuel it actually required to reach Edmonton.
The result was a 130-ton commercial jet turning into a glider at 41,000 feet. The pilots miraculously managed to land it on an abandoned airstrip in Gimli, Manitoba, which, by the way, happened to be hosting a go-kart race at the time.
It is a cinematic story, but the core lesson is terrifying. Physics does not care about your local cultural preferences for measurement. Gravity operates on mass. If your language for mass is ambiguous, systems fail catastrophically.
This is why the scientific community enforces the SI system so rigidly. A kilogram must be an absolute immutable standard everywhere on the planet. Historically, measurements were based on local objects, as the text notes. A foot was literally the length of a king's foot.
A grain was the weight of a grain of wheat.
Exactly. But you cannot build a global, collaborative scientific endeavor on biological variables. The standardization of units ensures that an experiment conducted in Tokyo can be perfectly replicated in Nairobi.
The textbook does offer a small, charming historical caveat regarding some of the symbols that have been universally adopted. It includes a short Threads of Curiosity section.
How about the speed of light?
Yeah, it reads, "Why is the speed of light denoted by c?" Scientific symbols often come from history and are based on international agreements, not necessarily abbreviations of convenience. For example, the speed of light is usually denoted with the symbol c, since it comes from the Latin word celeritas, meaning speed. Today, the speed of light is one of the physical constants, defined to be exactly 299792458 meters.
I always enjoy these historical artifacts embedded in modern science. It reminds us that science is not a sterile monolith handed down by a machine. It is an ongoing human conversation. We use C for the ultimate speed limit of the universe, not because it's intuitive to an English speaker, but because centuries ago, scholars used Latin as the lingua franca of academia.
The global community agreed to maintain that historical quirk for the sake of establishing a shared, permanent vocabulary.
Okay, let's take stock of the pedagogical journey so far. The student has learned to transition from observation to rigorous measurement. They have learned how to isolate variables by building simplified models. They've been given the mathematical language and the standard units required to articulate those models.
What is the ultimate goal of all this infrastructure?
The goal is to identify the underlying machinery of reality. Once you start running these models and sharing data, immense patterns begin to emerge. And categorizing those patterns is the focus of Section 4.
So getting into laws, theories, and principles, the text states, as observations are repeated, measurements refined, and ideas tested through experiments, we can organize our understanding of the world in a systematic way. In the secondary stage, you will come across terms, such as laws, theories, and principles, terms that have specific meaning in science.
Setting up the definitions.
A law usually describes a regular pattern observed in nature, often expressed using words or mathematical relationships. For example, Newton's laws of motion explain the jerk felt when a bus stops suddenly.
So that's the law.
Right. A theory goes a step further and provides an explanation of why those patterns occur, usually based on evidence gathered over time and available at that time. For example, the atomic theory explains how molecules are formed.
Moving from the what to the why.
Exactly. Principles are broad ideas that help us make sense in a given situation. For example, the principle of conservation of energy being applied when climbing up the stairs.
This is a critical point of clarification because colloquial English has completely mangled these definitions. Let's dissect them. A law in science is the what? It is an observable, predictable pattern.
Like the bus example.
Right, when you step on the brakes of a moving bus, the passengers jerk forward. That happens every single time. Newton's first law of motion describes that pattern. An object in motion stays in motion. The law provides the mathematical relationship.
But the law doesn't necessarily care why the universe is built that way. It just mathematically declares that it is.
Precisely. The theory is the why. It is the explanatory framework beneath the pattern. A law says, if I drop this apple, it accelerates toward the Earth at 9.8 meters per second squared. The theory of general relativity explains why. Because massive objects warp the fabric of space-time, creating a curve that the apple falls into.
And finally, a principle is a foundational rule that governs all interactions, like the conservation of energy. Energy cannot be created or destroyed, only transferred. I understand the definitions, but I have to point out that the naming conventions we use historically seem almost designed to confuse the public. If a theory is the deep explanatory framework, why do we refer to gravity as Newton's law, but evolution as Darwin's theory? Doesn't the word law sound more authoritative to the average person? It implies something unbreakable, while theory sounds like a suggestion.
You've identified a massive semantic trap. The historical naming conventions are absolutely a source of friction in public science literacy. Law sounds like a dictate from the universe, while theory sounds like a hunch. But in the scientific hierarchy, a theory is actually more complex and comprehensive than a law.
Right, because it encompasses the why.
Exactly. A law is just a single data point of behavioral pattern. A theory is the entire structural explanation that encompasses many laws.
The textbook explicitly addresses this dangerous semantic trap in the next paragraph. It states, do remember that in science, a theory does not mean a guess or an untested idea. It is an explanation based on careful testing and critical examination.
Such an important distinction.
It continues, these ideas are always open to improvement and often change as new evidence becomes available. This is a key feature of science that makes it reliable.
In daily life, someone might say, I have a theory about who left the coffee pot empty. What they actually mean is, I have a completely unsubstantiated hypothesis based on a wild guess.
Right.
But in the scientific lexicon, a theory is the reigning champion of explanations. The theory of evolution, the germ theory of disease, the theory of plate tectonics. These are not guesses. They have survived decades, sometimes centuries, of relentless testing, attacks, and critical examination by thousands of hostile researchers.
Yet the text highlights that the defining characteristic of a scientific theory is not its absolute permanence, but its vulnerability. It says these ideas are always open to improvement and often change. This seems paradoxical to many people. If a theory is the highest level of truth, why is it constantly being revised?
Because science is fundamentally an exercise in epistemic humility. Dogma demands that an idea is final and unquestionable. Science demands that every idea is contingent on the best available evidence.
So as tools get better.
Right. As our technology improves, as we build better telescopes, better particle accelerators, better magnifying glasses, we see new details. And when those new details contradict the old theory, the theory must be revised or discarded. The willingness to be wrong is the engine of scientific reliability.
And how do scientists actively try to prove their own theories wrong? They use them to try and see the future. The textbook explains this mechanism next.
Making predictions.
Yeah. It reads, one of the most remarkable strengths of science is its ability to make predictions. When laws, theories, and models are well established, they allow us to anticipate what will happen under new or different conditions before we can perform an experiment, and in many cases, even if we cannot perform an experiment.
Predicting the unseen.
Using ideas about motion, we can predict how far a kicked football will travel. Using knowledge of chemical reactions, we can estimate how much carbon dioxide will be produced, or how soft a baked bread would be. Using biological principles, we can predict how one's breathing would change while running.
Practical applications.
Remember that these predictions are not guesses. They are reasoned expectations based on evidence and careful thinking. When predictions match observations, confidence in the underlying science grows. But even more important, when they do not, scientists re-examine their assumptions, models, or measurements.
That feedback loop again.
And it finishes. In this way, prediction is a powerful tool that drives further exploration and a deeper understanding of the world.
Prediction is the crucible of scientific validity. If you claim to understand how a system works, you must be able to accurately predict its future state. If your model of chemical reactions is correct, you can predict exactly how much a loaf of bread will rise based on the volume of yeast.
Reasoned expectations based on evidence. That phrase separates a scientific prediction from a psychic reading. Let's look at the example the textbook provides to train the student in this specific type of thinking.
Let's hear it.
It reads, Example 1.2. How do we check predictions? Varsha told her friend Meghna, "It will rain this afternoon because the clouds look dark." Think of some questions Meghna could ask Varsha to make this prediction scientifically testable.
Okay, so a casual prediction.
The text gives the answer. Answer. Good scientific questions will look for measurable evidence and past patterns. Questions with simple yes and no answers are usually not so useful.
Because they don't give you enough data.
Exactly. Meghna could ask Varsha questions like, these are just examples, what was the condition of sky when it rained the last time? What is the humidity today? Was it above 80% the last time it rained? What is today's wind speed and direction? Is the temperature dropping like it did before the recent rains?
Those are fantastic questions.
It conclude, questions like these ask about measurable data and past patterns which go beyond mere clouds look dark.
Varsha's initial statement is a qualitative observation leading to a hunch. The clouds look dark, therefore it will rain. Is not scientifically testable because dark is a subjective assessment.
Right. Your dark might not be my dark.
Exactly. Meghna acts as the rigorous scientist here. She demands that the prediction be anchored in measurable variables. She wants the humidity percentage, the barometric pressure trend, the wind velocity. She is asking Varsha to build a data-driven model based on historical patterns to justify her prediction.
But let's pause and address a major source of skepticism for the general public regarding scientific prediction. If meteorology is a rigorous science built on data and models, why is the local weatherman so frequently wrong?
That is the age-old question, isn't it?
Seriously, if science can predict the trajectory of a spacecraft to Mars years in advance, why can't it tell me with 100% certainty if it will rain on my wedding next Saturday? The textbook actually confronts this head-on.
Oh, really?
Yeah.
How do they explain it?
It states, why do weather forecasts sometimes go wrong? Weather depends on many changing factors, such as temperature, pressure, humidity, and wind. Weather forecasts use measurements and models, but very tiny differences in conditions can grow over time and lead to something completely different. This is why forecasts are usually reliable for a few hours or even a few days, but less certain further into the future.
Ah, okay. This introduces the student to the terrifying reality of chaos theory, specifically the phenomenon known as sensitive dependence on initial conditions, commonly called the butterfly effect. Unlike predicting the orbit of a planet, which is a relatively simple gravitational equation operating in a vacuum, weather is a profoundly chaotic, non-linear system.
Let's unpack the mechanics of that chaos. How does a tiny difference grow over time?
Imagine you are running a massive supercomputer simulation to predict the weather for the next 10 days. You input the current temperature, humidity, and wind speed, but your thermometer is off by 0.001 degrees.
So tiny it seems irrelevant.
In a linear equation, that error stays tiny. But in a nonlinear weather equation, the output of day 1 becomes the input for day 2. The error is compounded. The 0.001 error on Monday becomes a 0.1 degree error on Wednesday, a 5-degree error on Friday, and by next Saturday, your model predicts sunny day, while in reality, a hurricane is making landfall.
Wow.
The math is executing perfectly, but the microscopic flaw in the initial measurement snowballs exponentially. This is why a 24-hour forecast is highly accurate, but a 14-day forecast is essentially fiction.
And the textbook uses that inherent limitation to teach a profound philosophical lesson about the nature of science. It reads, ready to go beyond. Even the most successful scientific theories have limits and may fail when new conditions are explored or when measurements become more precise. Such failures are not a weakness of science. In fact, they are its greatest strength. When predictions do not match observations, scientists do not reject ideas based on opinion or belief, but only on evidence. No scientific theory is ever final, and none is beyond question. This openness to being corrected by nature itself is what has allowed science to help us in understanding the world we live in.
Openness to being corrected by nature itself. That is the defining ethos of the scientific method. When a prediction fails, when a highly sophisticated weather model outputs the wrong result, the scientist does not view it as a defeat. It is a vital data point indicating that the model is incomplete.
The failure forces them to build a better compass. Nature is the ultimate impartial referee.
And this demand for empirical evidence isn't just for researchers in lab coats. The textbook explicitly shows how a ninth grade student can use this exact framework to navigate the modern digital world. It provides a real-world application for debunking misinformation.
Oh, this part is so relevant. The text reads, "Threads of curiosity, checking viral claims on social media. Is eating food harmful during an eclipse?" A commonly circulated claim is that food should not be eaten during an eclipse because it becomes harmful.
I've heard that one.
Disproof comes from asking simple scientific questions. An eclipse is just a play of shadows. What physical change occurs during an eclipse? Does temperature change significantly? Does food go bad if it is left in a shadow? You will conclude that no physical, chemical, or biological mechanism supports such a claim.
This is where scientific literacy becomes a functional shield against superstition and viral nonsense. The student is presented with an authoritarian claim. Eating during an eclipse is harmful. Instead of accepting it, they use their new pedagogical tools. They build a simple model of the event.
What is a solar eclipse? It is the moon passing between the Earth and the sun, casting a shadow.
And once you define the physical reality of the model, it's just a shadow. You apply the compass questions. Does food spontaneously rot when a regular rain cloud passes overhead and creates a shadow? No.
Does a temporary drop in temperature accelerate bacterial growth? No, refrigeration proves the opposite.
Exactly. By simply demanding a physical, chemical, or biological mechanism for the claim, the myth instantly disintegrates. You don't need a PhD to debunk it, you just need structured reasoning.
Which perfectly sets up the next crucial skill in the textbook. You didn't need to run complex equations to debunk the eclipse myth. You just used rough logic to see if the claim made physical sense. In science, that skill is mathematically formalized as the art of estimation. Let's move to section 5.
Yeah, the art of estimation. I'll read the introduction to this concept. The textbook states, as you continue your journey through science in grades 9 and 10, you will gradually develop habits of thinking that are useful far beyond the classroom. A helpful strategy is to first understand the situation being studied, then identify the quantities that matter, and finally make a rough estimate to check whether an answer makes sense.
Setting up those guardrails.
Right. Exact values are not always necessary, especially in the early stages of reasoning. Often, an approximate estimate is enough to tell us whether a result is reasonable or impossible.
This is so useful.
Learning to estimate helps you build intuition, detect errors, and develop confidence in your thinking. Science values careful reasoning, perhaps much more than accurate calculations.
That final sentence is a massive paradigm shift for a student. Science values careful reasoning, perhaps much more than accurate calculations. It directly subverts the traditional math class dynamic, where getting the exact decimal point is the only path to a good grade.
Absolutely. Estimation is about constructing a conceptual safety net. It is about building an internal bullshit detector.
Consider a student taking a physics test. They're calculating the velocity of a car rolling down a hill. They plug all the numbers into their calculator, but they accidentally miss a decimal point. The calculator outputs the answer. The car is traveling at 8,500 miles per hour.
Wow.
If the student lacks the skill of estimation, they will just write that answer down because the calculator said so. They trust the machine over reality. But if they have estimation intuition, their brain immediately flags that number. Cars don't break the sound barrier rolling down a hill. The answer is physically impossible. Therefore, a calculation error occurred.
You establish the boundaries of reality before you ever touch the math. Let's look at the real-world example the textbook uses to train this intuition.
Right.
It reads, how much rice would feed a family of 4 for a month? To make a rough estimate, assume that all their calorie needs come from rice alone. An average adult needs about 2,500 kilocalories kcal per day.
Okay, getting our baseline numbers.
Find out how many calories 100 grams of uncooked rice provides when cooked, and use this to estimate the daily requirement for the family. The aim is not to get an exact number, but to check whether the answer makes sense, as 100 grams for a month is clearly too little, while a few tons is far too much.
Setting the extremes.
Exactly. Such estimation helps connect science to everyday questions about food and resources and shows why approximate reasoning is an important scientific skill.
So the objective here isn't to calculate the exact grain count. The objective is to bracket the truth between two absurdities. Will 100 grams of rice feed a family of 4 for a month? No, they would starve in a day.
Will 3 tons of rice feed them? No, their kitchen would collapse under the weight.
The answer resides in the middle. 4 people at 2,000 calories a day is 8,000 calories. You figure out the caloric density of rice, multiply it by 30 days, and you arrive at a ballpark figure, maybe 30 or 40 kilograms. But the value is that if your math accidentally outputs 4,000 kilograms, your estimation skill immediately alerts you to the error.
Now let's look at the masterclass application of this skill. The textbook introduces what physicists call a Fermi problem, named after Enrico Fermi.
Oh, these are fun.
A Fermi problem is a brain teaser that asks you to estimate a seemingly impossible massive quantity by chaining together a sequence of smaller, logical guesses.
The textbook presents this brilliant activity. It reads, Example 1.3. Estimate how many liters of air you breathe in one day. Start by estimating how many breaths you take per minute and the volume of one breath. Your aim is not to find an exact answer, but a reasonable estimate.
Okay, so breaking it down.
Answer. At rest, we take about 12-15 breaths a minute, and there are 60 T924 equals 1,440 minutes in a day. So we take roughly 22,000 breaths, about 20,000 breaths a day.
So that's the frequency part.
Right. We also need to find the volume of air in one breath. One way to estimate this is to think that it takes about 4 or 5 breaths to fill a typical rubber party balloon, which when inflated has a volume of about 2 liters.
Oh, that's clever.
So one breath is perhaps about 0.5 liter. Hence, we breathe in about 10,000 liters of air a day.
This is an absolutely beautiful piece of cognitive engineering. Let's break down the mechanics of why a Fermi estimation works so well. When you are asked how many liters of air do you breathe in a day, your brain instantly panics.
Right, because you have no frame of reference for that. It feels completely unknowable.
But the Fermi method teaches you to fracture the unknowable mountain into small, manageable rocks. Step 1. Breaths per minute. You don't need a medical degree to know this. You just sit quietly and count your own breaths for 60 seconds. Let's assume 15 breaths.
Okay.
Step 2. How many minutes in a day? That's simple arithmetic. 60 minutes times 24 hours is roughly 1,400 minutes. 15 breaths times 1,400 minutes gives you a magnitude. Roughly 20,000 breaths a day.
That alone is a staggering insight into human biology achieved with basic multiplication.
But the true stroke of genius is how the textbook models the volume of a single breath. You can't see the air you breathe, you can't put it in a measuring cup, so you invent a physical proxy, a party balloon.
The balloon proxy is brilliant.
You know, a standard balloon holds roughly the same volume as a 2-liter soda bottle. How many normal breaths does it take to inflate that balloon? Let's guess 4. If 4 breaths equal 2 liters, then 1 breath equals half a liter. Multiply your 20,000 daily breaths by half a liter, and you arrive at an astounding conclusion: you inhale 10,000 liters of air a day.
But wait, I have to challenge the accuracy here. When we guess that we take 15 breaths a minute, or that a balloon takes 4 breaths to fill, those are incredibly rough guesses. What if I'm a marathon runner with a low resting heart rate who only takes 10 breaths a minute? Doesn't the inaccuracy of these tiny guesses ruin the final answer?
That is the exact magic of the Fermi calculation. The mathematical architecture of chaining guesses actually protects you.
Oh, so?
Let's say you slightly overestimate your breaths per minute, but then you slightly underestimate the volume of the balloon. When you multiply a string of estimations together, the overestimates and the underestimates tend to cancel each other out.
Oh, I see.
The goal isn't to find out if you breathe exactly 9,842 liters. The goal is to determine the order of magnitude. Are we talking about hundreds of liters, thousands, or millions? The Fermi method reliably lands you in the correct order of magnitude every single time.
And the textbook models the ultimate scientific flex. Verifying your own data using an entirely different method. It continues the paragraph by stating, now, it is hard to see if this estimate is reasonable or not. But if we go back to our balloon example, one could blow up a balloon in about 20, so maybe we could fill 3 balloons a minute.
Okay, a different approach.
Multiplying 3 balloons per minute by 2 liters per balloon by 1,340 minutes a day will give about 8,640 liters, which for estimation purposes is reasonably close to our earlier estimate of 10,000 liters. Naturally, we would get extremely tired very quickly after blowing balloons nonstop, unlike normal restful breathing.
This is the hallmark of rigorous intellectual honesty. You arrive at a spectacular number, 10,000 liters, and instead of publishing it immediately, you attack your own conclusion from a completely different angle.
Using the continuous inflation of balloons.
Right. The second method uses the continuous inflation of balloons over a 24-hour period. It yields 8,640 liters. In the realm of estimation, 8,600 and 10,000 are identical. They validate the magnitude.
It's incredibly empowering. It teaches the student that no question is inherently unknowable if you know how to break it apart. But as we reflect on that breathing problem, a larger question arises. When we solved it, what class were we actually in? We were calculating lung capacity, so it feels like biology, but we were using volumes and gas expansion, so it feels like physics. But we were doing multiplication, so it's math. Which is it?
The answer is that it is all of them simultaneously. Which brings us to the final unifying theme of this textbook chapter, the interconnected natural world. Let's read how the authors frame this concept.
Okay, the textbook states, after grade 10, if you decide to study science, it will be divided into branches like physics, chemistry, biology, and earth science, and even in grades 9 and 10, the chapters you have will focus on some of these areas. We've highlighted some of the exciting things you may learn about in the next level up boxes.
So acknowledging the school structure.
However, do remember that the natural world does not have any such boundaries. These divisions are made by us to only help organize knowledge. They are not independent of each other.
So important.
Most of the real-world problems today, such as understanding climate change, developing medicines, or designing sustainable technologies, require ideas from several disciplines together. Science also connects naturally with mathematics, technology, arts, and social sciences. To make sense of the world fully, we need to connect multiple ways of knowing and expressing ideas, each enriching the other.
This is a vital deprogramming of the modern education system. Schools are built on a factory model. You go to room 101 for exactly 50 minutes to do biology, then a bell rings, and you walk to room 102 for exactly 50 minutes to do chemistry.
Right.
It subconsciously teaches the student that these disciplines are isolated silos, but nature is completely oblivious to the human academic bureaucracy.
A towering redwood tree doesn't operate on a bell schedule. It doesn't say, okay, right now I am going to execute some biology by dividing cells in my roots, and then at noon I will switch over to chemistry to run photosynthesis in my leaves, and then later this afternoon I'll tackle the physics of using capillary action to draw water 300 feet up my trunk.
Exactly. The tree is a continuous, simultaneous explosion of physics, chemistry, and biology. The boundaries only exist in our minds because human cognition is too limited to study the entire universe at once. We have to put things in boxes to comprehend them.
But the textbook wisely points out that while the boxes are useful for basic learning, real-world problems require ideas from several disciplines together. If you want to cure a disease or reverse climate change, you have to take the concepts out of the boxes and weave them back together.
And the text provides an incredibly relevant, modern example of this interdisciplinary necessity. Let's read the final box.
The text states, ready to go beyond. How does a mask really work? Solving real problems requires knowledge from several branches of science. During the COVID-19 pandemic, we all used masks for safety.
A very familiar example for all of us.
Understanding how a mask works requires concepts from physics, particle motion and electrostatic attraction, chemistry, properties of polymer fibers, biology, size and behavior of viruses, and mathematics, modeling airflow and filtration efficiency.
Think about the depth of engineering hidden inside a simple N95 mask. The general public views a mask primarily through the lens of biology. It is perceived as a physical chain link fence designed to block a biological entity.
But a virus is microscopically small. If the holes in the mask were small enough to physically block a virus purely by size, you wouldn't be able to breathe through it.
Exactly. So how does it actually work? This is where the physics and chemistry take over. The mask isn't just a sieve. It is an active electromagnetic trap.
Let's detail the mechanics on that. The chemistry comes into play when scientists design specific synthetic polymer fibers. But the physics is the true magic.
Oh, definitely. Those polymer fibers are manufactured to be electrets, meaning they hold a permanent, localized electrostatic charge. Now, a virus particle floating in a water droplet might be electrically neutral, but as that neutral particle approaches the charged fiber of the mask, the electric field of the mask actually distorts the electron cloud of the virus particle.
It induces a dipole.
Right, it polarizes the virus. And once polarized, the virus is irresistibly pulled toward the fiber and sticks to it, like a balloon sticking to the wall after being rubbed on your hair. That electrostatic attraction is pure physics.
And then you add the mathematics. A mathematician has to model the fluid dynamics of human breathing. They have to calculate the pressure drop across the mask fabric to ensure that the air velocity is slow enough for the electrostatic fibers to actually grab the polarized particles before they get sucked through.
It is a masterpiece of integrated science. If you only have a biology department, the mask never gets invented. You need the whole orchestra playing together.
Which leads us to the concluding philosophical thesis of the entire chapter. After walking the student through models, math, chaos theory, and interconnected disciplines, the authors summarize what science fundamentally is. Let's read the final passage.
The textbook concludes, finally, as we have mentioned in every textbook, science is not just a collection of facts, equations, or experiments. It is a human activity shaped by curiosity, creativity, collaboration, and careful questioning.
A human activity.
It grows as people ask questions, test ideas, share results, and learn from mistakes. Science develops over time through the work of many individuals across different cultures and generations.
It's an ongoing process.
Even if you do not choose to study science beyond grade 10, scientific thinking will be very important in whatever you do. It helps you understand the technology that surrounds you and helps you evaluate information critically and make sense of the world you live in.
That's the real takeaway.
As you begin this stage of exploration, science invites you not only to learn about the world, but also to learn how we are trying to understand it. Embark on your journey of discovery, looking carefully through the magnifying glass of evidence and guided by the compass of curiosity. Happy exploring.
Science is not just a collection of facts. It is a human activity. Science is a verb, not a noun. It is the process of asking questions, acknowledging our own ignorance, testing ideas, and leaning on the work of the generations that came before us.
And the most vital takeaway is that this methodology isn't exclusively reserved for people who go on to wear white lab coats and operate particle accelerators.
Right. The textbook specifically states that even if you never take another science class after the 10th grade, this framework is your armor.
Exactly. The ability to demand measurable evidence, the intuition to estimate whether a statistic makes sense, the logic to debunk a viral myth about eclipses, these are the tools that allow you to navigate a complex, technologically saturated society without being manipulated.
We've covered a tremendous amount of ground today. We watched the curriculum transition the student from the phenomenological wonder of childhood into the rigorous quantitative demands of secondary science.
We explored the paradoxical power of deliberate ignorance, how stripping away the messy details of reality allows us to build functional models, like the subway map or Meghnad Saha's simplified star.
We saw how mathematics is just a highly efficient translated shorthand for physical reality, and how standardizing that language prevents catastrophic failures like the Gimli glider.
We define the hierarchy of laws, theories, and principles, breaking down the semantic trap of the word theory. We examined how predictions test those theories and how chaos theory and the butterfly effect limit those predictions in nonlinear systems like weather.
We learned how to wield Fermi estimation to calculate seemingly impossible numbers, like the 10,000 liters of air we breathe daily. And finally, we dismantled the artificial walls between the disciplines, showing how physics, chemistry, biology, and math all converge to build something as deceptively simple as an N95 mask.
It is a remarkable pedagogical achievement for a single introductory chapter. It arms the reader with a completely new lens through which to view reality.
As we wrap up this deep dive, I want to leave you with one final provocative thought to chew on. We spent a significant amount of time today dissecting the philosophy of deliberate simplification, how scientists intentionally ignore complex variables to build a model that answers a specific question. I want you to apply that concept to your own life right now.
Oh, I like where this is going.
Think about your career trajectory, or a complicated personal relationship, or a massive societal problem that is causing you anxiety. Are you currently feeling paralyzed because you are holding a magnifying glass so close to the issue that you are overwhelmed by millions of tiny, chaotic details?
That happens so often.
What is the actual core compass question you are trying to answer? And more importantly, what details could you forcefully, deliberately ignore today in order to finally build a clean, functional model of your situation? Sometimes the only way to mind your direction is to stop trying to map every single tree and just look for the horizon. Thank you for joining us on this deep dive. Happy exploring.